Hello everyone and welcome to today's webinar on the new SmartBox version 2 software. My name is Snellings and I'm a member of both the sales and the R&D team here at NeuroNexus, and I've been one of the people working on and helping to develop the new SmartBox platform. Today we're going to use the new V2 software to run an experiment. We're going to run that experiment with simulated data. It'll be distributed data across multiple channels. We're going to run that data into our SmartBox unit for a live recording, and we're going to use that data to demonstrate the different features of the new V2 software. We're going to go ahead and launch our SmartBox software. As you can see, there are three main panels that define the new V2 SmartBox interface. The leftmost panel is the control panel. The center panel is where the spike traces and the digital and analog input traces will be found. And the rightmost panel is the probe panel. That's where we will display a graphical representation of the probe that's used in these experiments, and it is what allows for the new probe-centric visualization experience of the V2 software. In the upper left-hand portion of the screen is the status feedback area. You can see right now everything is blank because our SmartBox is not turned on yet. However, once I hit the power button, we get the feedback to know that the SmartBox is connected with the head stage in port A. We're using a 32-channel head stage in this experiment with a probe that is 4 by 8, 4 shanks with 8 sites on each shank. There are two status windows on the SmartBox. The first is the virtual representation of the box itself, and then below that is a text message. And between the two, they give you the information that you need to know that the unit is up and working. And if the unit is not working correctly, then instead of a blue light here, this whole thing will flash red, and will let you know that there's been an error in the setup. Next, we're ready to go ahead and prepare for your experiment. So we will do that by moving into the SmartBox configuration area. So on the control panel, when we click on the SmartBox Configuration tab, we see that we get a menu come up with several different options. This is the area where you will set up the main parameters of what is recorded to your data files. Right here is the sampling rate. You can choose from a drop-down menu from as low as 1 kilohertz up to as high as 30 kilohertz. With the upper frequencies being the sampling rates used more for single unit recordings, and the lower frequencies more for LFPs or other signals such as, for instance, cardio signals. Below that is your hardware filter. This is key because it determines what data is actually recorded to the files when you hit save. The upper and lower bandwidth are both user input, and then you input your desired bandwidth, and then this is the actual bandwidth that the system calculates to correspond with your inputs. And again, these set the actual frequencies for what data is recorded to your data files. That's important because below there are some software filter options, such as the software notch filter at the bottom, that do not control at all or don't affect what's recorded to your data file. These software filters, such as, for instance, this notch filter to remove either the 60 or 50 hertz noise if you're plugged into the wall and getting electrical power line noise. This would only remove that frequency of noise from the display, so for visualization purposes as you're recording. Again, it will not affect what's recorded to file. The other options in this configuration menu are to set the cable length Neural Nexus offers links of 3 or 6 feet. And so in this particular experiment, we're using a cable that's 3 feet long in port A. So we'll stay with the default instead of switching to the other 6-foot option. And we don't have smart links connected to ports B through D. So we can leave them all at the default. And finally, there's the file path and file name. These control, the file path controls where your data file would be saved once you hit record. The default is to the public documents area. And if you're going to change that, we suggest that you actually open a File Explorer window and copy and paste the entire location so that no typo errors are made in inputting your location. But you do have the option of manually typing it in if that's your desire. And finally, the file name. The default is SmartBox Recording. That will be the base file name. And then in addition to whatever base file name you specify here, the timestamp of when your recordings start and stop will also be appended to the end of each file name. So even if you didn't change the file name at all and you just always use SmartBox Recording as your default name, each time you record, you will get a unique file name based on those timestamps. All right. Now that we're set up in the configuration area, we can close and we're just about ready to start recording. All right, the next step in the recording process, as you'll note, this area here, which is where the spike traces will be, is blank. As well as in the third panel, there's nothing where the probe representation should be. Before you can start streaming data, you have to choose a probe from this drop-down menu to represent the probe that you're recording with. As I've mentioned before, in this experiment, we're using a probe with 4 shanks and 8 sites along each shank. And you see, once a probe is chosen here, the spike traces show up here, and that's when you're really ready to record. When you own a SmartBox and Neural Nexus probes, any Neural Nexus probe that you use in an experiment should be found in this drop box. And if it is not found, or if you're using a custom probe, or if you buy a new probe type that you didn't have before, simply contact us and we'll make that map available and put it into the drop down so that you'll always be able to find the Neural Nexus probe of your choice when you're doing your experiments. And this mapping that is displayed here will incorporate all of the different maps that you need to keep track of for your recordings. That means your site map, your connector package map, where those sites translate to the connector. If you're using an adapter, it would also be represented here, such that while you're doing your recordings, you don't have to worry about any of those maps. The site that you choose on here should correspond directly with the location of the physical location of that site on the probe that you're recording with. And just for example purposes, let's take a look at a few of the other configurations, some of the configurations of different probes that might be available. We see here something interesting. You note that the probe that I chosen as drop down is an A 8x8, so it's a 64 channel probe. However, over here in our status, remember that I'm only using a 32 channel probe in this experiment. I'm only using a SmartLink 32 head stage connected into this port. So by choosing a 64 channel probe, the system lets us know that there is an error and that we chose a probe that could not possibly be correct. However, any of the 32 channel options available, such as this surface grid, the system would allow as legal even if it's not the actual probe being used. So you as the user would want to make sure that you choose the actual probe that corresponds with what you're using. And as I mentioned here, we're using this 4x8 probe. Now that we've got our experiment configured and we've chosen our probe from the drop-down menu, we're ready to start streaming data. So we return to the control portion of the screen, click Stream Data, and there it is. So, as I mentioned before, this is simulated data that's being run directly into the SmartBox. This data contains both LFP and in single unit data. But as we started streaming, what shows up on the screen is too large. The signal on the traces are so large that they're running into one another. So we will want to adjust the amplitude of each individual trace on the screen. So to do that, we'll want to look at our toolbox of options for controlling what we display on our spike trace channel. This toolbox has 5 different options. The default is to drag to scroll. That lets us move our data up and down to access all of the channels that are being streamed at a given time. If we right-click to return to that menu, the next option is the one that we want here, which is to zoom amplitude. We left-click to choose the tool, and then we left-click and drag. If you drag up, you can increase the amplitude even further, but what we want to do is lower the amplitude so that we can get distinct signals. There are other options on that toolbox though. If we right-click, there's a zoom spacing option. Again, left-click to choose, left-click and hold, drag upward to put more space between the traces, drag downward to put less space between. Right-click to return to the menu. The next option is to control both of those at the same time. You can zoom both the amplitude and the spacing. Again, hold and drag. And with this option, we were able to drag down and put all of the different traces that we're streaming onto the same screen at the same time. You see down here, these are all 32 channels. This option is available no matter how many channels that we're streaming with, up to the 256 channel limit of the SmartBox. So if we were using multiple head stages with a high enough channel count that we reached our 256 channel limit, we would be able to still choose this option and get all 256 channels on the screen simultaneously. The question is essentially how useful is being able to see all 256 channels or 128 or 64, however many channels that you're displaying. How useful is it to you to be able to look at all of the channels at once versus a subset of the channels? But that's a decision that you can make based on the resolution of your screen, the size of your screen, and just how distinct you want your different channels to be. In this case, we're looking at 32, and as you can see, each signal is pretty distinct. At least we can see the different slow waves on the different channels. However, in addition to just the LFP information that's found on here, we're also interested in trying to identify spikes. So to that end, let's hook up a speaker to our system so that we can actually listen to what's going on these individual channels. If I choose this channel and hook up my speaker, I can immediately hear popping sounds that indicate that there may in fact be a spike on this channel. As I click on different spike traces, each trace that's highlighted corresponds with the trace that we can hear on our speaker. Also, if you note visually off to the right, each time I click on a new trace, a new channel is highlighted on the probe. What this is telling us is that this trace that I choose here is located physically at this channel on the probe. This is one of our new unique features to always allow you to know exactly where you're recording from at any given time. So suppose we want to take a closer look at any of these channels. We're listening to them. Sounds like there's some popping there. There might be a spike. Let's take a look at what actually is going on there. We can do that with our spike scope. When you open the spike scope, you get this horizontal red line that's set as a threshold. You can move that threshold down, or you can move it up. And any waveform that passes that threshold is captured and displayed. The 10 most recent waveforms to pass that threshold are displayed at any given time, with the most recent one highlighted the darkest. So as we look at this, we see that popping does appear to correspond with a single unit. Because of that, that makes this channel one of interest for us as we're moving forward. We see on here that channel is located in this location on the probe, but perhaps we want to keep an eye on that channel moving forward in this experiment. We have that option. If we then click on this channel, you'll note that the location of the channel that I clicked on turned blue. The spike trace corresponding to that channel, which was channel 10, turned blue and moved to the top of the trace list. And also the spike on the spike scope also turned blue. So what this does is we can keep track of the activity on that particular channel very easily, even if we move to another channel. So now I've highlighted another trace. I want to see what's going on channel 5, but even so, channel 10 is still highlighted and at the top of the screen. Channel 5 happens to be on the same shank as channel 10, and we can see on the spike scope and here on our speaker that there does appear to be a spike on that channel as well. So if that also is a channel of interest, we can click on this one. We see that it's a different color scheme. Everything is orange. And so now we've got two traces at the top of our screen, channel 10 and channel 5, that we want to look at further. We can come down and look around for another channel of interest. And perhaps we notice on channel 14, hey, there's another spike there, and it's on that same shank. What a coincidence. Let's highlight this one as well, and you see you get another unique color. It's also at the top of the screen. We've got our 3 sites located on this shank that each have what appear to be good neural activity there. Maybe as I'm doing this experiment, I would say, you know what? This shank seems to be in a pretty good location. Maybe I would like to click on the other individual channels on this particular shank and see if there's activity on them as well. This is a good practical usage for this probe-centric approach because it lets us isolate particular locations of interest, physical locations of interest within our recording data set. However, there is more than one way to use this probe-centric approach. In a recent experiment that I participated in, instead of choosing individual channels of interest, let's come up here and clear our series. In this particular experiment, it was decided that we really wanted to know before we even started looking at the data exactly how the sites corresponded to each other. So in our panel 2 spike traces, instead of being ordered 1, 2, 3, 4, 5, 6, 7, 8, 9, we wanted to order them such that that each shank was numbered from top of the shank to the bottom of the shank in order. So we started with the leftmost shank, and instead of clicking on a site, you click and hold. Then you can drag down and until you let go, every site that you choose will be represented in the same color scheme. So when you finally let go, you have all 8 sites from the leftmost shank highlighted in blue and represented from top to bottom on your display menu. If you do that for all of the different shanks, then when you sit down and actually start recording, you have a convenient spatialized view of your spike traces or your potential spike traces, such that any unit or activity that you do see would be spatially represented in a way that makes sense on your display. So again, this is another practical way that you can use this spatial mapping feature to your advantage, particularly if these sites and or shanks are close enough together that a single unit might show up on multiple sites simultaneously. Finally, while we're still looking at this probe area, I should mention that there is another toolbox here similar to the toolbox that's found in the second panel. If you right click in the third panel area, the toolbox comes up. The top tool, the default, is the one that we've been using, where you reorder the sites and color the sites by clicking or dragging using this tool. You can also left click to choose the second tool, which was setting an active site, and that would work over here the same way that clicking on the spike trace worked over here. So if I click on this site, you see that it highlights the trace over here to show which spike trace corresponds with the location that we choose on this map. We can right click again, and we see that the third option that comes up is enable or disable site. What that option would be used for is if you are using a probe that you know has a bad site on it, or maybe it didn't have a bad site when it went in, but maybe there's just a lot of noise on that particular channel, and it's just kind of distracting you from the channels that are of interest to you. What you can do once you've chosen that disable link is if you come to a site on here, and let's see, right now we've got this site, channel 23, highlighted. If we now click to disable it, we see that once we disabled the channel on this display, channel 23 also disappeared from the main spike area. Suppose we didn't like this channel. We click, and again, that channel goes away. So with our enable and disable tool from this toolbox, we can, that's one way that we can remove potential noise or bad channels from our recording display. But there's another option as well. The second way that you can enable or disable channels is to come over here into this channel properties area. There are other things that you can do in this area as well, though. So for the sake of demonstration, we're going to stop streaming so that we can make changes in the channel properties. Yes, so for the sake of this experiment, we're going to go ahead and stop streaming so that we can look at what changes we can make in our channel properties area. First, when we get to the area, we see the same type of status feedback that we saw in the upper left-hand portion of the screen, where we've got a probe in port A, and it's a 4x8 probe, and we have no SmartLink head stages on any of the other 3 ports. Next, when you come down here, this area that begins with amp A1 and then goes into the channel numbers, these correspond with the traces shown in panel 2, and also with the channels on our probe model over here. So remember, we clicked and disabled a couple of channels, channel 23 and channel 2. You see that they're both show up as enabled or disabled here. You can also change them back from here. If you double click on the disabled, there's a drop down box. You can come back to enable it. That X disappeared from here, and when we return to the spike trace area, you would see that the spike trace is returned as well. We could also do the same for channel 23. Another option that you have here is you see this custom name. On the main, if we return to this string, we see each trace has a channel name next to it. That name corresponds with the fixed name over here. However, when you're recording, if you decide that you would like to make a note about a particular channel, like for instance that channel 9 might happen to have a really good spike on it, you can make that note here by changing the channel name to say spike A right shank. All right. When we return out to the stream, it hasn't changed on here. It's still called channel 9 on the display. However, when we record the data, instead of channel 9, it'll have your custom channel name displayed in your data so that you'll know, hey, this was a channel of interest to me. Finally, while we're here, I'd like to take a look at the digital and the analog areas. On the SmartBox, there are 2 digital inputs and 2 analog inputs that come standard on every SmartBox. However, if you buy a SmartBox kit, it comes with a breakout board that allows up to 16 digital inputs and 8 analog inputs. And so the SmartBox software has space available for all of those different inputs. So if we were using that breakout board, we could, for example, come here and enable multiple digital input channels that when we return to our main stream will show up at the top of the screen. You see now that there are 4 digital inputs displayed here, but we highlighted 5, and we also had those 2 analog inputs. If you move your cursor over this thin gray bar between the analog digital area and the head stage area, then click and drag, you can drag down to give more room to your digital and analog input area if that's of use to you. However, in our case, in this experiment that we're running, we weren't using any of the analog and digital outputs. So let's return to the channel properties, and we can go ahead and disable each of these channels such that when we return to our streaming area, we now see that those digital and analog channels are no longer on the screen. And if we come back to our horizontal gray line, we can click and drag upward such that the entire screen is dominated by our head stage data, which is of interest instead of the blank area. All right, so now that we've got our channel properties set up the way that we want them to be, we've cleared our analog and digital inputs off of our display screen. Let's spend a little bit of time looking at the spike traces of interest. So let's start streaming our data again. We've got our LFP and our single unit data. So now I want to look at the data on a larger time scale. I'm also going to spread it out a little bit. Now we're looking at the LFPs as well as the single units. We need a little bit more space in between. All right, great, good to go. So we want to look at the different options for the different time scales where we can look at our data. And I also want to look at the data closer to full screen. So I'll hit the little triangle to pop our map information off the screen. But I am going to leave my control panel open because I want to be able to access that. So the default time window for a given spike trace begins as 5 seconds. So this is 5 seconds worth of data. Now we have the ability to go down as low as 0.1 milliseconds worth of data on the screen at a time, or we can go as long as a full minute's worth of data on the screen at a time, depending on your experiment and what you're looking for. We've got some flexibility in here. Now suppose you wanted to look at a really short time window, say 1/10 of a second, and it's really difficult to see individual units. I mean, you can see them in here, but it's moving so quickly that it's difficult to mentally process where everything is. So we have an option called Snapshot Stream that if you click on it, it pauses the action and you can see what the units look like, and you can return the stream and keep it going. When you pause the stream, it only pauses what's on this display. As you'll note, if you can hear it, the activity is still going on. It's still streaming through. And if we were saving, it would continue to save in the background, so that when we return to stream, you return to live action, and your recording is uncut. So let's demonstrate that. Let's start recording. You notice if you hit the record button, you get a nice little display that counts down how long your recording is. So now let's snapshot. You see, our recording keeps going. We can still hear it in the background. We return to stream, and we're right back there. Let's go ahead and stop our recording. We're 20 seconds in. And let's go ahead and take a look at our recorded file. All right, now that we've recorded our data file, let's take a look at it. We told you earlier on in the webinar that the default location for recordings is public documents. And within our public documents, here's our file. You see this file is of the type of, it's an RHD file. We offer two different methods for converting RHD files into a method that might be more conducive for your analysis. The first is to open up MATLAB and run the MATLAB script that we provide to read in these files and unpack them into variables with the pertinent information that you could then either analyze further in MATLAB, or you could export it from MATLAB as a text file or a binary file, some type of file that may be more readable into your analysis method. That's one way. The other way is to convert it into a .nex, a Neural Explorer file. Neural Explorer files are also widely compatible with different analysis software. And to convert into a .nex file is very simple. You simply use the converter app that we provide. You would right-click and then choose the option to convert this file to .nex, and it's just that simple. All right, thanks for watching. This concludes our webinar on the usage of the V2 software for the SmartBox.